In this video, we're going to talk about the lab write-up for the roller coaster lab. The first thing that we have to know to do the lab write-up for the roller coaster lab are the different types of energy. There's two main categories of energy. You have potential energy and you have kinetic energy. Potential energy, when we talk about potential energy, we talk about stored energy. Energy that is waiting to happen. It's not currently happening, but it has the potential to happen. We can see a few examples of potential energy here. This would be an example of gravitational potential energy, right? Up here we have the Roadrunner. He is an elevated position. He's higher than the Coyote. If the Roadrunner were to move out, he would fall down. He's not currently falling down, but he has the potential to. Now we can see, unfortunately, for the Roadrunner, he's a whole lot closer to falling down. Here we have elastic potential energy. You have a spring that is all tightly coiled up. It's been pulled back and is waiting to snap. As soon as that mouse hits that trigger there, it's going to release the mousetrap. It has the potential to snap, but it's not currently snapping. And here we have chemical potential energy. Okay, in the dynamite, the chemicals, the atoms and the molecules have the potential to react. They have the potential to explode. Something that the Coyote may take advantage of here eventually. But it's potential, but is not currently exploding. So potential energy is the energy that is stored. It's waiting to happen. It's the opposite of kinetic energy. Kinetic energy is the energy that is happening. It's the energy of motion. It's the energy of what is currently happening. Okay, so here you can see Alice is falling down the well. Now, when we talk about Alice falling down, she had gravitational potential energy, and it's been converted into kinetic energy. She's now falling down. Fire, that chemical potential energy that we saw before, or maybe we had some logs of wood that were getting ready. They had potential to catch on fire, but this is actual fire. This is kinetic. This is the fire occurring. And the same thing with electrical. There was potential for the electricity to move through the light bulb and cause it to light up, but it's actually happening now. So the difference between potential and kinetic. Kinetic is energy of motion that's happening. Potential is energy that's stored. It's waiting to happen. It may, but it's not happening yet. Whenever we talk about energy, we need to talk about the law of conservation of energy. It guides everything that we have to do with energy. Just like we had the law of conservation of mass that said that mass cannot be created or destroyed, the same thing applies to energy. So what we say is energy cannot be created or destroyed. Okay, that's an important concept for us in this lab. As we look at our lab, okay, this is a typical roller coaster that we saw on the wall. We need to talk about where was there the most potential energy. And I think everybody agrees that the higher something is, the more potential it has to fall. So we had the most potential energy up here. So how did it get that potential energy? If we said that potential energy cannot be created or destroyed, it can only be changed. Okay, it can be changed. Then what changed to make this potential energy exist? Okay, well, how did that marble get set up there? Somebody stood here and put that marble up there. When they put that marble up there, they lifted it from down low to up high, giving it more potential energy. So how did it get up there? It got up there because somebody used their muscles. So where did their muscles get their energy from? If energy can't be created or destroyed, the energy for their muscles must have come somewhere. Well, what did that person eat for breakfast? Right? So let's say they had cereal for breakfast. Well, then that cereal came from wheat. Where did the wheat get its energy from? Ultimately, it ties back to photosynthesis and the sun. So energy cannot be created or destroyed. It can only be changed. So once that marble was released here, and it started to slide down and move down and loop down here, it was changing that potential energy into kinetic energy. So at what point did it have the greatest speed? So if we said it had the greatest speed right here, this is where it would have the greatest kinetic energy. So the most kinetic energy exists where it has the most speed. Okay, so that's an important. Kinetic energy is where it has the most speed. And the potential energy, where it has the most potential energy, is the highest, because it has the most potential to fall. Now in the back of your lab, we asked you to try thinking about if you had two marble types, a glass marble and a metal marble, which one would be faster? Okay, this is simply an exercise in making a prediction. So there's no right or wrong answer here. Make your prediction. Did you think that the glass marble would go faster or the metal marble would go faster? We then asked you to conduct the experiment and calculate the speed of the marble. You were asked to find the distance that the marble would travel and time how long it took for the marble to travel down your roller coaster. The next question here asks, what is the formula for speed? You may look at that and think, well, I don't know, we haven't really gone over that. But if you've ever seen one of these speed limit signs in the highway, then you know the answer. We say the speed limit is 50, what? 50, and I think most of us would agree that it's 50 miles per hour. And if you might remember from math, another way of writing miles per hour is miles over hour. That's what the per tells us. Okay, miles is a measurement of distance. An hour is a measurement of time. In our case, we didn't go miles for our roller coaster, but we did go meters. Or perhaps you used centimeters. Right. And we didn't go for hours, ours went for seconds. So in our case, the formula for speed is going to be equal to how many meters did our marble travel divided by how many seconds. Speed is equal to distance over time. Speed is equal to distance over time. Let's say we had these calculations as an example, that our course was 7.23 meters long. Now that's much longer than yours. And the time took 6.2 seconds. So what I would like to see when you calculate your speed is you have written down speed equals, our distance is 7.23 meters divided by the time is 6.2 seconds. Okay, it's very important that you write down the units. Now I don't need to see you show your work on the side and do long division. I would much rather you come over here to a calculator, 7.23 divided by 6.2 equals, and then we'll round that answer to the nearest tenth. So 1.166. If we're rounding the nearest tenth, we look next door. That 6 says to round up. So our answer would be 1.2, and our unit is written right there, 1.2 meters per second. And our final question on our lab asks, what happens if the marble were to fall off your roller coaster, which it did again and again and again, and then it would bounce. Why would it bounce? And it asks you to use Newton's laws to explain. So if we go over very quickly Newton's three laws again. Newton's first law says that an object in motion will stay in motion. So when you had your roller coaster, the object in motion, so you put the roller coaster, the ball up here, the object in motion would tend to stay in motion unless acted upon by an outside force. Sometimes there was a fold or something happened with your roller coaster and there was no outside force to make it go through the loop, and so it went straight and it rolled off. Okay. The second law says that if an outside force, an unbalanced force, acts upon an object, it will accelerate. Okay. Well, we knew that as soon as we released the marble, there was an outside force, gravity, that wasn't balanced, and our marble would begin to accelerate. So our marble starts to accelerate and fall down, or go through the course. And Newton's third law says that for every action, there is an equal yet opposite reaction. Okay, so if we had the floor down here, and our marble were to start moving because of Newton's second law, it has an unbalanced force which makes it accelerate, it starts to fall down. An object in motion will stay at motionless, acted on by an outside force. When it hits the ground, Newton's third law takes effect. Newton's third law says for every action, there's an equal yet opposite reaction. So you have the force of this marble coming down and hitting the floor. But that floor is also hitting the marble back. So there's an equal yet opposite reaction, which forces the marble to bounce up. And it'll keep bouncing. And you might say, how come the marble doesn't keep bouncing the same height forever? if energy can't be lost. But did you hear anything each time it hit? Clink, clink, clink. Energy was being transferred in other ways. There were small amounts of friction generating tiny little bits of heat when it hit the ground. There was sound because energy was transferred into the air, bumping air particles into one another, which we heard as a clink, clink, clink. So energy wasn't lost, no energy was destroyed, but the energy of motion was transferred into other sorts of energies, as you could hear your marble roll across the ground, and friction would eventually slow it.